Okay, first of all, thank you very much for the opportunity to speak in such a beautiful conference and such an event. And of course, somehow the subject of talk is very closely connected to what Ofer did over the years. First of all, Perverse sheaves, now he even admits that he is part of it. And also, somehow, I will talk about infinite dimensional generalizations. So, of course. Okay, so let us, I will write down a plan. One of the reasons why I want to write, because I know I'm not sure how far I will go, but first will be motivation. Namely, it will be finite dimensional situation. Second, I will formulate my goal. Third, I will talk about characters, categories of Lyadic sheaves on pressed X, or maybe infinity pressed X. Next, I will talk about somehow there will be some categories. Categories will be infinity derived categories or stable infinity categories. And next I will say about perverse T structures, perverse sheaves. On, let's say, nice pressed X. Namely, categories will exist always in very big generality, and in order to define perverse structure, we'll need certain smoothness kind of restrictions or whatever, or some finiteness restriction. Finally, I will formulate main result. And after that, hopefully I will get in order to this, because I will need somehow main result will use some stratification. And stratification we will need is Goretzky-Kottwix-Macpherson stratification. And the last ingredient I will want to, I'm optimistic, otherwise. It's impossible to you see, it's impossible to live in Israel without being an optimist. Smallness of Grothendieck-Springer affine resolution. But this is actually just dimension count, so it's not. Okay, let's see. Okay, first of all, let us start. First of all, motivation. So motivation, of course, comes from as you probably all have known, that I'm coming from representation theory. Namely, I want to apply some algebraic geometry and category theory to get concrete results in representation theory, and specifically something connected to Langland's program. So motivation is follows. So let G will be the usual connected reductive group over some algebraically closed field. Good example, algebraic closure over a finite field, if you really want to apply it to representation theory. Then I want G where G is adjoint quotient. Okay, and then you can consider yes, no, because somehow it's actually very nice notation, because there are three actions. One is the left, right, and adjoint. Actually, so at least this is self-explanatory notation.
So you need to slice of conjugacy classes?
No, it's a quotient stack. Okay, if you consider on the level of points, it will be conjugate classes, but it's also by group. Okay, it's okay. So far, it's art in stack of finite type. It will disappear soon. Okay, and then we will consider D is the category, that usual familiar category, which is D, B, C. Okay, L or L bar doesn't matter, where L is prime different from K. It's its usual derived category. And then it's
to define it, still some work to define it.
Yes, it is. Yes, but actually, I will soon give you a way that in some sense, if you work with infinity categories, that to define it actually you can do without no work. Essentially, we'll talk about it in a moment. You're right, of course. It's true, but somehow okay. And then it contains very nice subobject which is called character sheaves, which I'm not going to discuss now, but I'm going to introduce one important example, which I'm going to generalize, or at least try to generalize. Example which is called Grothendieck-Springer sheaf. Consider the following. Consider B cross B, which is the same as adjoint quotient where B is Borel. And what is the Grothendieck-Springer sheaf, which I will call S? Is just pi of maybe I want to say that somehow this is a very nice stack, which is smooth of dimension 0. In particular, there is a very nice sheaf here, which is dualizing. The constant sheaf is dualizing sheaf are just the same, no even shifts and twists. So it's D of B. And Springer sheaf, of course, is of whatever, QL. And all the functors will be derived. I will not write R in any point, okay? And this morphism, of course, is proper. So I can put either Shiriko star, but at the moment at least, but I will put this one. Now, what is known about this sheaf? Okay, known is then. What is known as is perverse. Second, you know that S is minimal extension, where J is embedding into G regular semisimple. Regular semisimple. This is the second property. Third property is that double affine Weyl group. So let us, I will say, even stronger assertion. The set of automorphism of S is just equal to the W, which is Weyl group of G. No, automorphism, not endomorphism. Group of automorphisms.
No, but if you know if you know the automorphism, the endomorphism algebra, which is a QL algebra, the automorphisms form the units in this QL algebra, which is bigger than.
Oh, yes, that's what I want. Okay, let's say you're right. Yes, okay. This, of course, was what I actually need. But of course, yes, endomorphism is a affine Weyl group, and moreover, if you have an irreducible representation of W, then you can consider the isotypical component. Let's say in this case it's finite group, and the characteristic is 0, so it does not matter. So I will write down the reason I'm writing down because I have in mind something for the affine setting that most likely I will not have time to talk about this. But okay, so this is irreducible Perverse sheaves. Okay, And this, of course, example of the character sheaves. And more general character sheaves, you do similar thing, except you replace here B over B by P over P by parabolic subgroup. And you replace the constant sheaf by the sheaf which is pullback of the Caspital local system, whatever it is, which George defined and studied for many, intensively. And of course, somehow this is more general. Okay, now the question is, what is so first part was okay. Now we are going to our goal. Goal to extend everything to the affine setting. Okay, so I want to, so what does it mean I have to extend? I want to extend this, then I want to extend this, then I want to extend this. Okay, Springer sheaf and this result. And the answer is that it's possible to do it. There is some small modification. Okay, first of all, G you replace by what? By the loop group of G. What is the loop group of G? Which is the loop group of G. And what it is, by definition, loop G is a functor from algebras over K to sets. Right? And what is LG of A? Is by the definition is G of A of T. Okay, so as a functor is defined, now it's known by. I am not good in history. Probably Gerd was the first one who wrote it carefully, but I'm not sure. So I don't want to. So that's somehow it's int. It's int scheme, but int scheme in a really int scheme, namely that's somehow not like in the previous talk. In the previous talk there were int scheme, but it was inductive limit of finite dimensional varieties. Here it's really okay. Now you can do. Now you can let us try to generalize. What you want G over G? G over G you want to write the same thing. Okay. Now you can ask what it is. And the answer it is you was a functor from affine K to what? You just want to groupoids. Namely, you just take every A goes to. So LGRA is a group object. So this is just I will write group point action of the group by the group, or if you wish, it's the category whose objects are here. Okay, and actually I will talk, and later I want to say that of course later I will use the remark that its groupoids will be part of the infinity groupoids. Or what is the same as spaces. Now you can ask the following questions. Can one define? Can one define? First question. What is the D of LG over LG? Second question, can you define this element S? Grothendieck-Springer sheaf. Third question, can you define the can you define perversity structure? And 4 is S is perverse. And question 5, let me put the same thing. Just, mean perverse and, maybe some others. Question 5 says that yes, what I want. Okay, maybe you know what I will say even more here. The question is whether I want here, whether I want here. This is defined by affine while group. And question 5, let V will be representation of, let us say, irreducible representation. Irreducible representation of affine while group. And you can ask whether you can ask SV by using similar formula, whatever it means. First of all, can you define it? Whether is okay, defined, perverse, and irreducible. Okay, so far I formulated some questions, and now let us trying to give answers. So first I will give answers. Excuse me?
When you form the LG mod LG, there's no sheafification that you're doing, right?
No sheafification. There is no need for sheafification, and I will comment on this later, because later I will talk about sheaves, and then yes, you're right. What is the main idea I learned from a paper of, I guess, Dennis, that somehow that you don't need to sheafify. Sometimes it's better not to sheafify things. Okay. So at least for certain questions, it's easier. Then you can ask what happens whether something changed after you sheafify. And fortunately, in our case, the answer would be no.
You mean the group point itself doesn't change after?
No. The group says yes, but the category of sheaves wouldn't change. Category of sheaves would not change, wouldn't somehow before sheafification, after sheafification would be canonically equivalent.
Yeah, it is more like stackification or infinite.
Yes, okay, yes. Sheafification means stackification. Yes, you're right. Okay, now let us say answers. This is joint. It is our joint work on partially. I mean, it's not written, so it's almost done. But I will write in progress to be on the safe side. With Alexis Boutier and David Kashdan. Okay, first of all, answers. A1, A2. So its answer to this question is answer is yes. Okay, A3, A4. The answer is yes after some modification. And in a moment, I will say what kind of modification you will need. And what is the reason? Okay, and answer 5. Okay, first of all, it's okay. First of all, this is SV is defined. Most likely, meaning that somehow it is. So we are sure that it is, let us say, conjecture, or let us say almost theorem, but not in the sense of almost mathematic. SV is perverse. Okay, namely that there are somehow, okay, we have a reason, but we don't. There are some technical details to check. But what is not true? SV is not irreducible. Not irreducible in almost all cases. For example, take G equal SL2 and take V equal sign representation. If I take sign representation, it would not be irreducible. It would contain two irreducible summands, and actually I'm not sure it is semi-simple. Most likely no. Okay. Anyway, this is something that we have to carry out. For example, on the other hand, we do know the answer is for V is trivial. It's very easy to answer. The answer is yes. It would be reducible.
Can it also be 0?
For some, can it? also be 0? The answer is no, because we know over the regular semi-simple, over the whatever, over the locus where the reduction is regular semi-simple, it's a regular representation. No, like in the case, like in the finite case, over the regular semi-simple, it's just the regular representation.
Okay, so there you get what you should get. Yes.
Yes.
Particular non-zero.
Yes. In particular, it's non-zero.
You are working with representation of the affine very good, or
yes, I see. No, as I say, in the affine case, it's also true. In the affine case, it's also true. Over a nice locus, it is precisely the regular representation, and you can ask whether it's extension. Okay, I will, in a moment, I will say you.
Affine value group has a big translation part, so what does it mean, the regular representation?
Regular representation? Even infinite group has a regular representation.
On the
it will be infinite dimensional. Yes. Like Dennis constructed, it will be not constructible. Okay, it will be, okay. This D would be not constructible, it will be inconstructible. Yes. No, in a moment I will define the category. No, it's definitely not constructible. You can ask, okay, good. Oh, okay, yes. Maybe I want to comment on this. What you do is the following. Let n, which is not the same as n, which is actually maybe n is a not good notation, but it's what is called nilpotent column, but nilpotent I mean topologically nilpotent, but actually in our case it's not even topologically nilpotent, but the set of elements with okay, let us say with LG will be the set of locally closed whatever sub int whatever scheme such that I will write what is it's a point. Let us do notation. Let f will be k over t. So LG of k is of course the same of g of f, and you want that I will say you what is n of f. Okay, what is f valued point? Not f valued point. K valued point. It's the same as g into g of f, such that the g is regular semi-simple. And also I want that the characteristic polynomial, let's say g is bounded. Let's say g is bounded. But this is the same as characteristic polynomial has coefficients in OF. And I hope to get to a point that I will define it properly. Okay. Again?
The determinant is invertible or something.
Yes. Determinant, yes, is invertible. Okay, maybe I want before. So yes, and now what is? Let me write down precisely what I mean almost, and answer. Okay, and answer 3 says the following, that there exists perverse structure on what?
Why is it called n?
Because I don't know what is a better term. No, it's bad terminology. Any suggestions I will accept, but after the lecture. I don't know, but it's, okay, I say somehow n is because it's like topologically nilpotent, but actually it's even not topologically nilpotent. It's bounded. I don't know what's the bounded. No, but B is overused. I don't know. B is Borel. I don't know. Okay, anything. Okay, let us call it this. Okay, so we have a perverse structure on D of LG. You can ask why why this condition, and the answer is as follows. We will see later when I explain the perverse sheaves. Somehow our spaces are very, very infinite dimensional because they are not only infinite dimensional. There is the int part and pro part. Okay. And it turns out that the pro part is not a problem, but the int part is a problem. So let us consider the quotient LG divided by LG. Then both LGs has int part. And in some sense, this is both of them cause the problem. And you want somehow to kill these int parts. And now what I claim is that if you consider n modulo LG, that we essentially killed both int parts. Because here, this n with this characteristic polynomial is bounded. And here is that all the stabilizers are not bounded, but they bounded up to some lattice. But we are Ital topology, and Ital topology is, if you have discrete stabilizers, it's not a problem. No, because the stabilizer is what? The stabilizer of each point, it's what? It's the loop group of the centralizer, which is a torus, right? So it have the pro part and it have a lattice part. Lattice part is not a problem. So this is the reason. So our restrictions has actually there is a good reason why we need it. Of course, it would not explain why we need so somehow why it gives a structure, because we need more somehow. Formally speaking, we're using more than this.
But if you consider a torus with values in not necessarily reduced string, the loop group, I mean, you can have in the loop group some.
But it's a Ital topology.
Okay, so
It's a Ital topology. Nilpotent we can disregard. You're right. You're right. There are plenty of you're right. There are plenty of nilpotents which has to be taken with care, but fortunately they not affect the Ital cohomology. Okay, now let us start. Okay, the next. Now we want the part number 3. I want to give categories of Vladik. Oh, is it maximum? Yes. It's maximum. Okay. Yes, and here I am very fortunate that Dennis gave talk before, and before he did part of the hard work, except we need actually more general setting. But not much more general setting. It will be categories. Okay. Categories of Eliadic sheaves. On infinity prestack. Okay, first of all, what is infinity prestack? Oh, prestack. Yes, maybe I want to say that because, despite of the fact that all the objects are infinite dimensional, but I personally, very ignorant person, I only know what is the Eliadic sheaf on the variety of finite type of a field. Even moreover, here I even need only variety of a fine variety of finite type of a field. And the idea is that actually what we want to do, we want to start from this finite dimensional situation and then apply category theory and hope it will solve all our problems. It does not happen, unfortunately, but in some sense it does. Okay, so what is infinity prestack? Infinity prestack is a functor from affine. Oh, just a minute. What I did, I want what was before. Before it was algebras. I don't know what I say. Affine opposite to infinity groupoids, which is the same as spaces. Okay, and actually, at least all the prestack. Okay. The prestacks that will actually appear will take values in the usual groupoids. But if you want to develop the whole theory, you would better to use this setting. Now you want to say that now for every goal, for every this prestack.
of course, the functor is also in some sense.
Yes. Okay. No, it's not pseudo functor. Okay, the functor should understand in the following way. You can ask what are the infinity groupoids or spaces form. Its form infinity category. Yes. This is a category, in particular infinity category. It is a functor of infinity categories, whatever it means.
This is a big thing because there are many people who work on what is in infinity category. So.
But nowadays it's what? No, but let's ignore it because there is no. I want to some. I'm not okay. I want to convince you that if you use the language of infinity categories, then everything becomes much easier. But of course, if I cannot do all the details, Well, let us assume that infinity categories are like categories, which is the correct way of thinking. And there are some thousands of pages that people, Ludi, etc., wrote. So in some sense, nowadays the theory is rather settled down. Okay, of course one has to be careful. You're right. And maybe I will even point out the points where one has to be careful. But still, Prostek is certain functor. For example, the Prostek we will be interested in is this one, LG divided by LG. At least you kind of understand what it is. Okay, let's do it. Okay, for every Prostek, our goal will be to define certain category, which I will write it, namely somehow there are actually several choices. There are at least, actually will be two categories, this one and this one. This means constructible will be small category, and this will be the big category. And big category, for a big category, there are four choices, kind of, because you have to choose its category with respect to Schrick or star, and you want int or pro. And for some reason, I will use same terminology as Dennis. No, actually, by the same reason, probably as Dennis. But I maybe want to say just the remark that if you want something like sheaf functions correspondence, then it's better to consider Verdier dual version. In a sense, Verdier dual version will be actually star and pro.
So the choices that you mentioned, the four ones, give different categories?
Yes, it will be different categories. Two of them will be Verdier dual, but two of them are not. Will be Verdier duality, but it's not Verdier duality within one category.
Between the pair?
Yes.
And the other pair is not?
It's also. But somehow the other pair is somehow less useful somehow. There are reasons why this choice is better, and of course one of the reasons is Dennis explained it. For example, that this is that Schrick has a left adjoint. Okay, and Dennis explained that there was a general, the category of sets. It's not self-dual. Set is not equivalent to set opposite. And it's therefore left adjoint and right adjoint. There are some different features. What? Okay. Okay, let's start. Okay, so what we do the same. The procedure is as Dennis indicated. Case A, let x will be, let's say, affine. Actually, affine does not need affine a type of k. Then we define dc of x is dcb xql, but I want to consider the corresponding enhanced version. So the infinity derived category, whatever it means. Okay, I consider this one, and also the other one will be just the int. Okay. Then what is important that all the 6 operations, or at least four functors, can be lifted to upgraded to the setting. In particular, for every xy, there exists a functor which I say, as I told you, the main functor for me is this one, the Schrick pullback. Okay. So far, so good. Okay, except of course this is almost the same category, except as I said that it's not a triangulated category, but it's what's called stable infinity category. Now the next step is you want to say let x be affine. But for affine schemes, x is a limit over xi, where xi is affine of finite type. Right? And then what you do, you define d of c of x is by definition is co-limit. Actually, I was careful enough, it creates colimit in the category of categories. Except, okay, when diagrations, all the colimit will be homotopic limit, and I don't want to. So everything would be homotopic limit, or if you wish, in other words, somehow the infinity categories call. So there is infinity category of infinity categories, and in the infinity categories, in every infinity category, there is a notion of the limit. And so this is the limit inside of this infinity category. What?
Infinity category.
Yes, yes. Yes, but so there's something homotopic limit. Despite that, of course, in the applications that we had in mind, actually, what happens that x this functor would be fully faithful, and then you can really define everything on the level of triangulated categories. Then the homotopic limit is actually the same as colimit one used to. Yes, but now what's important is colimit with respect to, yes. And now claim is it is independent. What? Yes. It's just a pullbacks, yes? Star pullbacks. As I said, our main functor is a star pullbacks. You have a projective system here. You have an injective. Shriek. Shriek.
Push, no, but the colimit is relative to
Oh, pullbacks. Sorry, pullbacks. Sorry. So our only operation would be, okay. So it's independent on the presentation. Okay, it's independent on the presentation. Now, okay, this is this. Okay, now functoriality for any x morphism from x to y of affine schemes. There exists a okay. Sorry, I forgot. Okay, maybe I will say this in a moment. There exists a natural functor from d of y to d of x.
But since you're doing it over a filtering category, probably the homotopy colimit, because the higher derived direct limits are 0.
No, why?
At least for abelian groups when you have a filtering category. So I'm not sure. Is it the case that on just the level of naive triangulated category?
No. So it's not fully faithful map. It's not fully faithful. It's very important.
If you pass to homotopic categories there, it's also still a homotopic colimit, no?
No. What's it say? No. I'm pretty sure. Okay. So okay. If this is fully faithful, no. If this is fully faithful, the answer is yes. In general, I'm pretty sure that the answer is no. I cannot give a counterexample on the stop. No, the transition maps. If all the transition maps would be fully faithful, then the answer, of course, would be yes. Otherwise, I'm pretty sure that the answer is no. But let me not.
Because it does not.
No, say I'm not good in finding counterexample on the.
No, but I don't know the definition of the colimit.
Okay, no, there is a notion. Okay, no, as I said, send is the following. The correct definition is as follows. Okay, you want what?
But
Compatible system of some kind and limit of this.
Yes, some.
There is
Okay.
this is
Okay, maybe you know what? Maybe what Peter asked is correct, but I'm not sure. in this.
You are working in some world of replacing triangulated categories by what you call stable infinity.
Yes.
You didn't say what it is, so we cannot. I mean, if I don't know it already, I cannot know what.
No, but
it's a colimit in this sense. I think.
Okay. Suppose you have a category, usual category. Then there is a notion of colimits inside this category. Yes. There is a certain diagram you can Now, what I claim that suppose your category is infinity category. Yes. Then there is also the same, essentially the same definition which says that inside of infinity categories there is a notion of colimit. Now, what I say is that this of guy is a stable infinity category. But stable infinity categories form an infinity category. And you form colimit inside this infinity category. Whatever it means.
Yeah, but I'm really sure that on the level of homotopy categories,
It might be okay, but maybe it's correct. You see,
it just means part of the usual.
Yes. No. It's definitely false. So it's definitely false. Okay. Each object comes from V. What is the mapping space? The mapping space take two object here and take the mapping space. And you want colimit of mapping space. It doesn't commute with taken by 0.
It does. It's a filtered colimit. It's filtered. Filtered colimits.
Sorry. Then it is. You're right. Yes. No. Okay. Okay. You're right. Here. Yes. You're right. Here it is. But anyways, there is this one. Okay. Now the question. Okay. Now the third is let x be any pre-stack. And then what you do is the following. Yes, maybe the only thing it's better to do it here. And I want to say what is what is d of x is the int dc of x. Or it's the same as colimit in the same sense that Dennis explained it in the previous talk. It's colimit of d of xi's, but in the sense of colimits inside of categories which has all co-complete. Yes. Now, okay. Okay. C is okay. Then somehow C somehow let now x be any pre-stack. Then we define what is d of x. I will write something, and then I will explain what is going on. The question: take any morphism, take d of a, where a is affine. That is to give an element object in the category. It is the same thing as is for every you want for every morphism from the affine scheme to x to give its d of a, which is functorial in a.
And of course it is in less Samaya.
Not just factorial, but compatible really with pullbacks.
Yes. No, compatible with pullbacks, yes.
And also Samaya coherence.
Yes, of course. Yes. No, yes. As I said, limits here is everything. No, it's limits of infinity category, but limits somehow it's actually a rather usual operation in the sense that it limits you essentially can calculate naively.
No, not at all. Like here is a really lot of coherences in there.
Yes and no. No. The index sense it's complicated. What is the object? No. You cannot spell out. It's true.
No. Like the colimit is easy, but this limit is extremely complicated.
Okay, it depends what to call. Okay. Let us give example which is give example which is compatible. I mean, if you want to spell out, you need infinitely many data. It's true. Yes. But then you even don't try. Compatible with pullbacks. Let us say example. What is suppose you have some. Let us say even do the more general situation. It will be even easier. Let's gxx everything is finite dimensional affine. From this follows we want then of course LG goes to LX. then you can consider what is the derived category on LG of Lx modulo LG. Okay? And then you can ask how to calculate it. And the answer is that actually it's sort out that it's easy to calculate, and you write the same bar complex that people would assume. It's somehow d of Lx Lg limit of what? D of Lx d of Lg g of Lx okay. And it does not matter whether you put arrows in this direction or not. But now, what's important somehow? Somehow it's true that somehow usually you consider the derived category on some complicated object of the simplicial schemes, and usually it's a very complicated object. Here you, in some sense, do the same, but you package the difficulties differently. You just write the same diagram as before. This is the usual bar complex. And you just take limit, but limit has to be taken in the appropriate sets. If you try to spell out it, it's impossible. But in some sense, it's even advantage you even don't try, because the only thing what you have to do, you have to use some certain properties. And why? Okay, if you wish why, and the reason is that Lx modulo Lg is just co-limit of this diagram. And this is after you spell out the definition. It's essentially it's almost a tautology. If you write down what is the definition of colimits, and you use that colimits in the colimits commutes with base changes, then somehow it's just remember that we are in the category of functors, am I right? So you should check any your test affine scheme, and you calculate its value here and value here, and then it's just somehow general nonsense. Calculation. So it just needs some functorial properties. Yes, and this from this is essentially a tautology. So this is kind of definition of what it is. The only somehow the advantage of infinity category is that if you try to do in the derived categories, in triangulated categories, there is no limits. You cannot even write this thing. You can write, but usually it doesn't exist. There's no limits inside triangulated categories or limits of triangulated categories. Okay, now let us somehow. How I get. Okay. Now you can ask, what about perverse sheaves? Okay, as I said, somehow on perverse sheaves there is an essential difficulty, because you see, perverse sheaves, it's something about, in the definition of perverse sheaves, there is a dimension involved. And here everything is infinite dimension. You can ask what you can do in order to overcome it. Okay, but let's start. Perverse sheaves on some rest x. What you do, of course, the same thing that we did before, but then you have to be a little bit careful. Okay, first you won't let x be usual finite dimensional, let us say affine, which is not necessary for finite type of a k. Then you can ask the following. Okay, then your d of x has a perverse T structure. The problem is that now you want that this T structure nicely behaves in a functorial way. Problem is that if even you take the nicest possible morphism, which is smooth, no, nicely smooth, then is somehow T exact only up to homological shift. Right? Because there is some homological shift, and therefore, if you take limits, it will be infinite homological shift. It's not good because we don't want to get something. But there is of course the very easy solution how to overcome this problem. Solution: we consider I shifted perverse structure. So let us say, for example, let us say X will be equidimensional. So what you do, you just apply a homological shift in order to make it compatible. So you define, you say that D is dB is, let us say, I shifted perverse. If and only if the F, I hope I do it correctly, is perverse. For example that you have to make in mind, the dualizing sheaf is perverse in this new shifted T structure. Sorry. If X is smooth, then you want the dualizing sheaf is perverse. This is what? X to the, it's QL, twice dimension, right? And you want to check when this perverse, the answer is when you minus this, it will be perverse. So it just shift it in the correct direction. But now what is nice about this is that somehow the shift only depends on the x. So for every x you know how to shift. Of course there is some small technicalities what to do in the not equidimensional situation, but I don't want to discuss it. It's possible to do it, and unfortunately there is more than one solution, which I don't like. I mean, there is one solution which is true in general, but there is other simple solutions which would have worse functoriality properties, which is enough for many applications. But nevertheless, what we do, we just take the usual perverse structure, and then you shift it by dimension. Then, okay, this is what we did for the, let's say, for the finite type. Now B, okay, definition, let X be, okay, say X, so definition, let X be an affine scheme X is called placid if X can be limit of xi of finite type at all transition maps are smooth. For example, there is all the some example. If you take, let's say, L plus of G, or let's say any R groups are of this type. So it's just projective limit of something which is all the transition maps are smooth. Which is limit of what is called an LG or something like this. But in this case, we defined, Okay, in this game there is a claim, which is actually easy exercise, to see that what is our category? Our category that we know that dx has a unique T structure such that all transition maps, such that all maps for all are T exact. Now why? Because I forgot whether this exists. Oh, it's already. Yes, because what is this guy? This guy it's colimit over dxi. So what do I say?
No, but if you shift all of them, then by the same integer. Then
No, it's not the same integer. It depends on x. On every x, I change it by the dimension of x.
yeah, but in the claim you say all maps projection after shape.
Yes.
Exact.
Yes. No. But T exact with respect to shifted T structure. In shifted T structure, the shift depends on the xi.
Okay. You are doing yes. Yes. So this is the equidimensional case question.
Yes. Okay. I say it's possible to do it not because it's actually locally equidimensional case, but actually you can do it even in general. But let me ignore this issue because anyway have to finish very soon. Okay. And now let us put C. And now what is the functoriality? Functoriality says the following. Okay. Easy claim. If x, y is pro-smooth, then is T exact. No, it's essentially general nonsense because. And now we want to do the somehow general case. Okay. Now you want us to do something which is not a affine case. But let us do example, which is essentially what we do. Let x will be equotient ex by r. No, I mean quotient x by r. Where we have the r is okay. Where you want that x and r. Oh, sorry. R is what it's pro-smooth groupoid. In placid affine schemes. Okay. Okay, let's not discuss what is pro-smooth. But you can say it's the following. I guess somehow for this purpose, it's enough. It's enough to show this is the inverse limit of finite dimensional. This is infinite limit of finite dimensional, and you can use that there exists a presentation such that it's the inverse limit of the smooth maps. Okay, this is and this is enough for this purpose because you remember somehow all the categories are coming from finite dimensional level. In particular, everything actually comes from finite dimensional level. Okay, let us do of placed affine schemes. Then what you want to say is that d of xr, which is remember what it was. It was the limit over dx d whatever. It was r d of whatever. What was r rx etc. Right. The quest has unique T structure such that what you want that its pullback is T exactly. And the idea is very, very simple. What you want? You want, for example, you take any object here. You want to write it as exact sequence of less than equal and greater than equal. Take it here. Consider this diagram. Take it, pull back here, and pull back here. Here, and here, you have already T structure. So you know how to decompose this, to decompose this as an exact sequence. And now the fact that all the maps are pro-smooth means that they're compatible. So you define, for example, that, I don't know, the corresponding exact sequence here as the limit of the corresponding exact sequences here. Of course, one has to write it, but it's essentially formally follows. OK. And now I have roughly zero time. But OK, yes. And now maybe I will say D. The last time, unfortunately, our space N is not like this. But now assume that our space X has a stratification Xi such that all Xi has T structure. Then what I claim is there is a general thing which is called gluing, that you can glue T structures on each of the Xi's, and then you get the T structure here.
Why is it not I mean, aren't you basically in the setup where G is acting on X, finite dimensional affine, and aren't all these maps from Lx times Lg to Lx, etc.?
Again.
Right, but even on Lg mod Lg, why is it not pro-smooth there?
Which one?
If you want to apply this to Lg mod Lg, are you not in the situation where this is pro-smooth groupoid in this sense?
No, because it's int. If it's L plus, if it would be in the case of L plus, everything would be perfect. No. If it would be in the case of L plus, everything would be perfect. I say our problem is that LG is not smooth because affine Grassmannian it has an inductive limit of projective schemes which are not smooth. So LG is not smooth. This is the problem. Okay, and then somehow say this has stratification, and then there is by gluing. We are done, and maybe one last thing. What I want to say, I will just one last sentence. I will say what is the affine Springer sheaf, and say that what is the yes. Let us say affine Springer sheaf, and okay. What is affine Springer or Grothendieck Springer sheaf? Of course, what you do is the following. You consider it's I over I, where I is the corresponding Ivachori, or maybe L plus of I. There is a map from LG to LG. There is a projection. Now the claim that this map is int proper in inappropriate sense. Yes, actually, it's beta n because it's compact element, so you get up here, and actually you need regular semi-simple. You remember somehow n was a regular semi-simple condition. So you want then first of all I say that this has a left adjoint projection, and you define S is a projection of the corresponding QL bar sheaf here. And the assertion is that first of all, it's possible to define a T structure. Namely, it has a stratification by the guys which we defined before, almost up to some nilpotents that I didn't have time to discuss. And then it's also, so the assertion is it is perverse and equipped with an action of the affine Weil group. Thanks.
There have been already many questions. Some more questions.
I mean, how critical is it that you use shriek instead of star pullback to define everything? Because in this closed smooth setting, the two don't really differ, right? The two derived categories together.
Critical. No, okay. The question, first of all, the question is, what does it mean, critical? It's more convenient. Okay, you can ask whether you can define everything. Okay, many of the things here it's let's say the situation is follows. You should decide whether you want to work on arbitrary press-texts or on press-texts with some condition, because our press-texts are essentially somehow finite dimensional up to some pro-unipotent. And pro-unipotent actually does not matter. For those, probably it's not very much different. In general, it's more convenient to work with this one. But on the other hand, many of the results can be translated. And of course, I did not talk about the proof, but actually, in some point, you need that for the perverse, you need the shriek stock and the star stock. So in some sense, we need some kind. You need more operations. I say that shriek pullback exists always. All the others exist only under some assumptions. So the answer is, let's say, I don't. Okay, you can ask whether I can do it for star. I did not check it. Possible. The answer is yes.
But then there is the indirection for when you take star. This is one problem.
No. But then of course you have instead of taking the shriek shifted, you have to star shifted. Of course. Okay. There is a good chance that everything would work. In general, shriek is more convenient and okay. By the same reason that Dennis explained, there is a difference between right adjoint and left adjoint. But I'm not sure. Let's see.
Okay, so I invite you to continue the discussion for research.